I'd like to introduce a concept known as P-series, which is really something that we've already kind of looked at just a little bit if you watch the Harmonic Series videos and the integral test videos. But this is going to be something that kind of continues to build on that. So P-series are series of the form 1 over n to the p power. Okay, so you know, they might start at 1, they might start at 2, it doesn't really matter what they start at, but something like 1 over n to some power, okay? That's what a P-series is. And again, we've already seen these previously. We saw a P-series in the integral test video. It was 1 over n squared, okay? That was one with a p-value equal to 2. And if you remember, that series converged, okay? We're also pretty familiar with another P-series. The other one that we're already familiar with is the one 1 over n, which of course is the harmonic series. Of course, this is the same thing as 1 over n to the first. So this is one with p equal to 1. And if you remember, that one was divergent, okay? If you watched the integral series, the integral test videos, I also did a series 1 over n to the 1/2 power, or 1 over radical n. That of course was one with p equal to 1/2. If you remember, that one was also divergent, okay? And so I wanted to come back and look at that just a little bit more carefully. Since I've already done a lot of examples, I'm going to kind of assume that you've seen those. And if you haven't, go back and look at those integral test videos. Anyway, I'm going to take a look at one additional one. This is not going to be a complete proof, but it will kind of generally address the concept. So anyway, a pretty typical P-series would be something like 1 over n cubed, okay? And so if you start listing that out, of course, this would be one with p equal to 3, okay? And if you start listing out individual terms, just to kind of see what's happening, you've got 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, and so on. And you can see that the individual terms are going to drop very quickly, okay? So the individual terms will approach infinity. If you apply the nth term test here, the individual terms the individual terms will approach 0 according to the nth term test. So we have the possibility that it converges, but we don't know that for sure. And so this would be a great one to do with the integral test. You could look at the related function 1 over x cubed dx between 1 and infinity. And of course, that's going to be 1 over x to that's going to be the same thing as x to the -3rd power. Okay, so the antiderivative there, of course, is going to be -1/2 x to the -2, and we're going to be evaluating that basically between 1 and infinity. I'll tighten that up in just a second here. Anyway, this form is not very good for evaluating integrals, especially improper integrals that are going to involve limits. So I would encourage you to put that x squared in the denominator and do it like this. And so what we're really looking at here is the limit as, I should really call this b, looking at the limit as b approaches infinity. If we apply the fundamental theorem here, that would be -1 over 2b squared minus -1 over 2x squared. Sorry, should be minus a negative there. And of course, that's this is going to end up being plus 1/2. If you apply this as b goes to infinity, you're going to have constant over infinity. This is going to approach 0, and this will converge to 1/2, okay? Again, that doesn't say that the sum of the series is 1/2, it just says that the series is convergent. So the P-series, the conclusion here is that the P-series with p equals 3 ends up being a convergent series, okay? Anyway, have not totally proved this per se. However, the breakpoint here, if you noticed, when I looked at a p-value of 1 and I looked at a p-value of 1/2, those were both divergent series. When I've looked at a p-value of 2, when I've looked at a p-value of 3, those are convergent series. And that actually is how the P-series will work, okay? For the P-series, it's going to be convergent for p-values greater than 1. And it's going to be, all p-series will be divergent for p-values that are 1, which would be the harmonic, or less, okay? And of course, all multiples of p-series will be either convergent or divergent based on what their comparable series would be. And we'll look at that a little bit more when we look at the comparison test in the next lesson. I'm going to put up a slide that shows the official definition of a p-series, but I think I've pretty much covered the high points here. Here's the official wording for the p-series. Basically, if you have a series 1 over n to the p, actually that should use series notation. That should really be a summation there. But anyway, if you have something of the form 1 over n to the p, it's convergent if n is greater than 1, and if n is equal to 1 or less than 1, it is divergent. And of course, the harmonic is a good example of that, where p is equal to 1.